3 more classes this semester. So I'm going to concentrate on the eigenvalue problem by 2 by 2 matrix. 这个2乘2矩阵的这个本征值问题。Okay, so it is a problem to solve A and lambda. A is a column vector, lambda is a value, we call it eigenvalue, and A is called eigenvector, by which I mean that matrix times A is equal to the number A, lambda times A. Okay, so it has a very, very obvious geometric or diagrammatic meaning. That is, when you multiply a matrix with a vector, usually it gives you another vector. That's the basic meaning of a matrix. A matrix times a column vector equals to another column vector. Usually, the final products are not the same. Are not the same as the original one. However, for certain cases, for very special cases, the A times the vector will becomes a number times the vector itself. That means that the products is the same as the original vector, except for a constant, which we multiply in front of it. Okay, so therefore, these vectors are very, very special. So that's called, we give it a name, eigenvector, and the number, the multiple, you multiply the vector by is called the eigenvalue. Okay, 所以呢，这个本征值的问题呢，最基本的就是当你把这个矩阵呢乘在上面的时候，通常呢一个矩阵乘在一个向量上面会得到另外一个向量。OK， 好，那通常就像上面的这个图一样。但是呢，在很多很特殊的情况之下，那个我好像不应该一直讲很特殊，因为每一个矩阵就是会有两个嘛，我应该再稍微再那个 moderate 一点，好，温和一点。那就是在两个很特殊的情况之下，这两个这个向量呢，你会找到两个向量。当你把这个矩阵呢乘在上面的时候呢，你的结果会跟原来的这个矩阵呢是成正比的。好，所以成正比的意思就是说，你乘上了一个数了以后，就会跟它相同。或者 in other words, the final product vectors will be it will be in the same direction as the original one. 如果你用那个向量的这个3度空间向量的语言来说，那当然啦，我一再强调的这个 the vector here are not 3-dimensional or 2-dimensional， 不一定是这个那个二次空间里面的这个向量 ，OK， 所以当我讲说它是同一个方向 in the same direction 的时候 ，I'm using 我是在用一个不对的语言 ，OK， 好，但是但是用这样的语言呢，可以让大家比较容易能够了解这个eigenvalue problem 的这个情况 ，it helps，OK， 好 ，so that's why I'll keep saying that A times a vector will produce another vector which is in the same direction as the original one. That's the essence of the eigenvalue problem. And I solve it. We use the 2 by 2 matrix as an example to illustrate how we solve this kind of problem, eigenvalue problem. So A times A equal to lambda A. We usually pull everything to the left-hand side and try to solve A. And you can observe if the matrix in front, A minus lambda 1, has an inverse vector matrix, then the only solution you can get for A, this vector A, can only be 0. Okay, we have already shown this last time, actually for 3 times already. Okay, and therefore, but 0 is not the solution we want. Okay, 0 is just nothing. Okay, therefore, we want a non-trivial, usually mathematician will call it a non-trivial solution, which means it is not 0. If you want a non-trivial solution, the only condition, there will be a condition that must be satisfied, which is that the determinant of A minus lambda I is 0. Okay, only in this kind of case, the inverse matrix does not make any sense, because the inverse matrix could be easily determined by this formalism. Is this expression, okay? And observe that there is a determinant s in the denominator. Therefore, the only way for this to make no sense is the determinant s is equal to 0. So that gives you the condition or the requirement for number lambda that we will have an eigenvector. This master equation will have a non-trivial solution for A. Do you see the point? Okay. Therefore, we can solve lambda. Please observe that this determinant is actually a second order algebraic equation, 二次的这个方程式. Okay. Therefore, this lambda has two solutions, no more, no less, 2, because it is a 2 by 2 matrix. Okay. Therefore, for these two numbers, we will be able to determine the vector A, so-called eigenvector, Yeah. And just by concentrating on the master equation, remember this is the master equation we start with. So with lambda determined, then you plug in and determine A, But you are only able to determine A up to a constant C1, because the equation actually, originally you thought there will be two equations. However, the two equations are just identical. Therefore, actually you have only one equation. So therefore, there are two numbers. Therefore, you can only determine the ratio between them. For this case, 0.2 times A1 is equal to 0.3 times A2. Therefore, I can only determine A up to the ratio between them. Here, I chose 0.6, 0.4. Of course, you can choose your own. Okay, as long as they are proportional to 2/3. Okay, yeah, you can of course write 0.2 here and 0.3 here, or 2 and 3 here. It's just that the constant will be different, yours and mine. Okay, yeah. Therefore, again, and the final solution will of course be the same. Okay. So that is to say, you can only determine the eigenvector up to an undetermined constant, but that's okay, because eventually, when you want to solve use this eigenvector to solve the equation, you need to plug in the initial condition. So that initial condition will help you determine this constant, just as we have shown various example earlier in the class. Okay. Therefore, now we have determined A1. So for lambda 1 equal to 1, this value, we find the eigenvector for here. I almost missed it. So for lambda 2, another solution of the condition 1/2. Yeah, maybe I should not say it's a condition. It's actually a name. This A minus lambda I equal to 0 actually has a name. It's called characteristic equation. Okay, it's called characteristic equation. Well, it's just the name for an equation that helps us to solve eigenvalues. Okay, but it appears very often in literature, so maybe it's easier. I will just say this is characteristic equation from now on. Okay, so when you solve the characteristic equation, there are two solutions. One, I can determine its corresponding eigenvector. The other one, I can determine its corresponding eigenvector. So for one eigenvalue, there corresponds to one eigenvector up to a constant. Okay, so I got two sets of solution. Two sets of solution of A for each value of eigenvalue. Okay, yeah. Therefore, that's the essence of solving the eigenvalue problem. Any question? You can observe that, of course, here I use the 2 by 2 matrix as an example to illustrate the procedure. And you can easily generalize all the procedure, every step by step, to 3 by 3, right? That's what you did in the last homework. In the last homework, I asked you to do the same thing, for a 3 by 3 matrix. Okay, I'll review that part later, maybe in the next hour. But some of you can do it, or you can most of you can do most of it. So it means the procedure here can be easily generalized to 3 by 3 matrix. We got 3 eigenvalues and you got 3 eigenvectors. How about 4? Of course, if it is a 4 by 4 matrix, then there will be 4 eigenvalues because the characteristic equation will be an algebraic equation of the 4th order if it is 4 by 4 matrix. Is it okay? And therefore, there are 4 solutions. And 4 solutions correspond to 4 eigenvalues. Every eigenvalue corresponds to 1 eigenvector. So it's so mechanical. It's so mechanical. That's the beauty of mathematics. It's so mechanical, so boring, so abstract. But that's also the beauty of it, because you do it once, and you can generalize the procedure to n equal to 3, n equal to 4, n equal to 5, n equal to 6. Of course, nobody wants to do that. But in principle, when the equation rises, you need to do a 6 by 6 matrix eigenvalue problem. You can do it, right? Okay, you can just generalize the procedure. Here, I have a very short. If the review here is too long, then there is a very, very short step-by-step procedure. Step 1, step 2, step 3. Okay, you can just do step 1, step 3, 2, step 3 for the question, for the problem you have in your mind. Okay. The only question is that the key, of course, is the polynomial. Here you call it a polynomial, which is the so-called characteristic equation I mentioned earlier. The determinant of a minus lambda I equal to 0. Okay, that's the characteristic equation we use to determine eigenvalues. However, if n is large, then to calculate the determinant will be formidable, will be very hard, right? You try. We did it for 2 by 2 matrix in class. You did it for your homework for 3 by 3 matrices. However, do anybody know how to do it for 4 by 4? Yeah, in principle, yes. But in practice, it's so hard. Okay, so usually most of the application, okay, you are going to encounter in physics studied, usually is constricted, is restricted to 3 by 3. I don't remember encountering any problem for 4 by 4 and 5 by 5. But I don't know. Maybe in your career you'll meet a problem for a 6 by 6, 7 by 7 problem. Maybe AI could do it for you. But remember, you are the master, so you have to tell AI, that's what I need to do. So step 1, step 2, step 3, teach your AI. Then you can do the problem. And for AI, calculating the determinant of 7 by 7 matrix is 7 by 7. That means there are 7 elements, okay, on each side, okay. So it's not a big problem for machine. For you, it's difficult, but for machine, it's easy, okay. But remember, okay, so that's the key idea. I have to tell you again, emphasize again, everything I talked about today, last week, could be easily generalized to n by n matrix. Okay, even though some of the tasks will be difficult to calculate, however, in principle, it's doable. In principle, it's doable. Just follow step 1, step 2, and step 3. Okay, you may, after all these gestures and discussion, you may ask yourself, or you may ask me once again, why are we doing this? Why is the eigenvalue problem important? Of course, it's important for physics. I've shown you already. Yeah. For solving this eigenvalue problem, I solved the couple oscillation. So I'm going to review again for 3 by 3 matrix in 1 hour. Okay. However, for mathematicians, these eigenvalue problems really has a mathematical importance. That's what I want to emphasize again. Last week, I mentioned the information in the eigenvectors and eigenvalue alone could represent a matrix. This is the ultimate importance of the eigenvalue problem for mathematicians. See, because easily if I have the information, if I know the eigenvector and eigenvalues of a matrix, or you can hide the matrix itself from me. Just give me the eigenvector and give me the eigenvalue. Actually, I can give you back the matrix. Let me put it in Chinese so that you clearly understand what I mean. 现在假设呢，我不知道这个矩阵是什么样子 ，OK？ 但是呢，你偷偷藏了一个矩阵在自己的手上，但是呢，你告诉我它的本征向量，你告诉我它的这个本征值。我是一个数学家，我很厉害，我就可以用这里所秀给你看的这个方法，我会告诉你说你的这个矩阵等于多少。Okay, that's so important for mathematician because that means all the essence of the matrix is stored in the information of eigenvector and eigenvalue. The trick is like this. Any vector could be decomposed into a linear combination of A1 and A2. A1 is one of the eigenvector, A2 is another eigenvector. So I will show very soon that any vector could be decomposed into C1, a constant, times A1 plus C2 times A2. I can give you an example here. 0.8, 0.2, any vector I chose. You can choose another one, and then you get your C1 and C2. However, I choose 0.8, 0.2. I say it will be equal to one eigenvector and another eigenvector. These two eigenvectors is what I got in the earlier for this A. Okay, 0.6, 0.4. And the eigenvalue is 1. Okay, another 1 minus 1. The eigenvector is 1/2. So I use this example through all my presentation. Okay, now, so if I chose any vector, 0.8, 0.2, you can choose your own and do the exercise. Then you can decompose this into a linear combination of this plus this. Okay, I will show you how to determine C1 and C2, but you know how to do it, right? Because this equation means 0.8 is equal to C1 times 0.6 plus C2 times 1. The upper elements must be the same. Then lower elements must also be the same. So 0.2 must be equal to C1 times 0.4 plus C2 times minus 1. So it's a systematic algebraic equation. 它是一个方程组嘛，对不对 ？So 这是一个方程组，那么它自然就有一个解。So I can determine quite easily C1 is equal to 1, C equal to 0.2. And this procedure could be reproduced for every vector you choose. Okay? So let me say here the x, any vector, in this case 0.8, 0.2 is equal to A1 plus 2A2. So now I showed you that I can use this information and the information about eigenvector and eigenvalue. You don't need to tell me A. You don't need to tell me the matrix. But I can show you that the A acting on X, A times X, could be easily calculated like this. It's easy. When you multiply A with X, or A times X, then this X, as I have shown, could be decomposed in this form. So it is A times this plus this. But according to distribution law, it could be written as A times A1 plus A times A2, and then add them up. Okay, that's a basic idea of a linear operation, right? And then when A meet A1, I usually say it's a frog meet the princess. When the frog meet the princess, it becomes a prince. So when A matrix meet A its eigenvector, it becomes lambda 1. It's a number. Becomes a prince. Okay, I'm sorry, a prince, right. And then, or on the other side, at the other term, this matrix meet the A2, its eigenvector. Again, when flock meet the princes, it becomes a prince. So it's a lambda 2. Okay. Again, a matrix times its eigenvector is the same as eigenvalue times this vector. Okay, so there's no more matrix. Everything are numbers and the vectors. Okay, so therefore, I don't know what A is, but I know A times X must be equal to C1 lambda 1 A1 plus C2 lambda 2 A2. Lambda 1, lambda 2, I know because you need to give me the information of eigenvalues. A1, A2, I know because you need to give me the information of eigenvectors. And C1, C2, I use the information when I decompose the vector X into two linear combination of the two eigenvectors. So C1 and C2 contains the information of X. So lambda 1A, lambda 2A contains the information of matrix. C1 and C2 contains the information of X. I don't have any idea what X is, A is. However, the action of A on any vector could be calculated. Okay? You don't need to tell me what A is. You just need to tell me X. Then I give you the final result, A times X. Okay? Wow, I mean, mathematicians like this kind of tricks. Okay? That means the essence of the matrix is contained in eigenvector and eigenvalue. Or put it another way, all the information, the essential information of the matrix A is contained in these two. So that's why it's called characteristic vectors and characteristic values. As I told you, eigen is a German word. Originally it means characteristic, or in Chinese, 特征，它的特征，所以 yeah, 特征 Is there a better English word for this? Probably not. So that's why if you look at the older textbook, some of the textbooks still call eigenvector characteristic vector. Okay, so that means if you have this characteristic of a matrix A, then you can reconstruct the A. You got everything you need to know about this A. Okay, this point is very important for mathematicians. So let me emphasize again. So eigenvalue problem is not only important for physicists. It is actually the essential problem that mathematicians want to solve in linear algebra. Okay? Any question? If not, I'm going to move forward. This is a very, very short review of what we have. I say, or I warn you in advance, this will be the most abstract and most mathematical lectures in our whole year. Okay? Nothing will be like this anymore. However, because this is a course of physical mathematics, therefore I need to give you some taste of how the mathematicians are viewing all the material we are teaching in this class. OK， 你们要学一点点看数学是怎么样子来讨论这样的事情。OK，for mathematicians, everything is about theorem, proof, definition. It's so boring, it's so mechanical, but it's useful to us. Okay, so you just take it like a medicine. Okay, a medicine for you, you don't like it, but it's good for your health. 所以呢，这样子的这个数学的思考的方法，你可能会觉得非常非常的抽象，非常的机械化，因为你可以看得很清楚。在我们这个讨论里面呢，没有什么生的东西，没有什么活的东西啊，所有东西几乎都是 concepts. It's about concepts and the logic. It's boring, it's abstract. However, it's useful. Okay, get used to it. Okay, get some idea about it. Okay. 好，今天呢 ，so today I'm going to get more and more mathematical. Okay, until maybe for the next hour, and then we come back to physics. Okay, and then we come back to physics. So I'm going to teach you, and diagonalization is very important. I don't want to review again. but remember this is important. Okay, there is another homework today. It's already listed on the net. This is, I think, problem 4. This is the final homework you need to hand in. Due May 21st. In the problem, I think, yeah, that's correct. So the first one is about diagonalization. I think the second one is also diagonalization, and more and more, and more eigenvalue problem solving. Okay, and if you are familiar with the procedure, then it will be much easier than the earlier homework because it's mathematics. Okay, it's just mathematics. Okay, so diagonalization, it is very important. I covered already, so I don't want to go back again. Today, I'm going forward to our final question in 2x2 matrix eigenvalue problem. Let me ask a question. In the discussion up to this point, actually, I assume that for our couple oscillation problem, K1, K2, and K3 are equal, or these 3 springs are the same spring. Okay? However, we can also put different spring at the various spots, right? So that means K1 could be different from K2, could be different from K3. Then use the same formalism. The matrix A will now be written in this form. Okay, you can adjust K1, you can adjust K2, and you can adjust K3 and get any matrix. As long as it is symmetric. I'm going to come back to symmetric again, but I covered it already. Symmetric means if you flip this matrix, it's the same matrix. So you exchange you exchange this element with this element. And you can observe that it is identical element. So if you exchange them, the matrix is still the same. Okay, in this way, this matrix is called symmetric. It's called symmetric. It's very, very important property. You will see very soon. So for this general problem, we could have any matrix as long as it is symmetric. Okay, so let's generalize our earlier procedure to this kind of problem. However, the generalization is so easy, right? Almost every step will be the same. You can just solve the eigenvalue problem of the new matrix in your question. And you get your eigenvalue, you get your eigenvector. Every eigenvalue corresponds to an eigenvector. And for every eigenvector, yeah, and therefore you can solve the problem just as in the earlier case. Oh, yeah. In the earlier case we did last week. Now in this transparency, but that's okay. That's okay. But the key question is that. Backward too much. The key question is the following. The key question is the following. When I solve this problem, again, let me review it a little bit. This is the equation of motion written in the matrix form. And then I assume the solution is A1, A2 times exponential I omega t. And you plug in this form into the equation, you get A times A equal to omega squared times A. So I say this omega squared is the eigenvalue. Sometimes I call it lambda. Or in your homework, maybe you will call it lambda omega 0 squared, okay, to make your calculation easier. Anyway, so this is the eigenvalue problem for this new generalized matrix, okay? Then I solve it. According to our procedure, you first go to the characteristic equation. The determinant of A minus lambda I equal to 0. And I say that this equation is an algebraic equation of the second order. Therefore, it has 2 solutions. Omega 1 squared, I call it omega 1 squared, omega 2 squared, or if you prefer, lambda 1 and lambda 2. But the point is, well, omega should be a real number. If omega is not a real number, then this exponential I omega will have exponential I omega t will have a exponentially decreasing function inside. It's not what we expect, right? Because this is just an oscillation system with no friction. 根本没有摩擦力啊，它就是一个简单的这个振动问题啊。Okay, therefore you expect this problem to be oscillating, not decaying. Okay, just as the first part of our lecture. It's not a 衰变问题，这不是一个衰变问题。Therefore, this omega beta is real. If it's not real, we got problem. But what we have until this point, the characteristic equation is second order, only guarantee there are two solutions. Not necessarily positive, not necessarily real. Okay, so our task in the following 1 hour, maybe half an hour, is to prove that the eigenvalue I got, this lambda, or I should say lambda 1, lambda 2, are all real and then positive. I need to prove it's real. They are real and positive. Otherwise, this formalism doesn't work. Got my point? Okay, that's a very, very important mathematical question. It's not just a physical question. Mathematicians better help us to solve this. Okay, so I'm going to prove two theorems. Very mathematical, very abstract, very mechanical. Follow me. So the first theorem, or I should say the first two theorems, are that all eigenvalues of a symmetric matrix are real. I'm going to prove that. So the first step, of course, please observe that the matrix we encounter is a symmetric one. Again, if you flip this matrix, this element is equal to this element, so we call it symmetric. So this property is only true for symmetric matrix. Okay? So I can prove, or mathematician can prove, a symmetric matrix has all n real eigenvalue. First. The second, also as part of the theorem, I can also prove that all the n eigenvectors can be chosen to be orthogonal. By orthogonal, I mean they are perpendicular to each other. Let me give you a counter example. For example, this is 0.8, 0.2, 0.3, 0.7. That's the matrix we are working for a long time. And then the eigenvector is 0.6, 0.4, and 1 minus 1. You can easily convince yourself they are not perpendicular. Okay. By perpendicular, I mean when you multiply or taking the inner product of A1 and A2, to do that, you multiply 0.6 by 1, 0.4 by minus 1, and add them up. Okay? So 0.6 times 1 plus 0.4 minus 1, of course, is not 0. Okay? So in geometry, we'll say that they are not perpendicular, or they are not orthogonal. But this is not a symmetric matrix. How about symmetric matrix? Here, I showed you an example of a symmetric matrix, 9, 3, 3, 1. You can follow the same step. It's exactly the same step as before, so I don't want to go into detail. But you can practice again by solving this eigenvalue problem for this matrix on your own. So the eigenvalue of this symmetric matrix are 0 and 10. The first eigenvector is C1, 1, 3. The second eigenvector here is ZC2, 3, minus 1. You can try to solve the problem yourself. Usually, we want to choose this constant C1 so that the length of the vector is equal to 1. For example, for this 1, 3, I would like to choose this C1 to be equal to 1 over square root of 10. That's okay, right? So it is easy to check the length. The length is the square. The length square is equal to the square of this element plus the square of this element. Okay, just like usual geometry. Okay, so therefore I usually want to choose the C1 so that it is the length is equal to 1. So this is the way to do it. For U2, this is the way to do it. Again, it's 3 minus 1, so C1, C2 is actually the same as C1. The point is not C1 and C2. The point is, if you multiply U1 and U2, taking the inner product, it is easy to show they are perpendicular to each other. 1 times 3 plus 3 minus 1 equal to 0. Okay, so we will say that the two eigenvectors are orthogonal. The two eigenvectors are orthogonal. It's a property for symmetric matrix. You can see again, for non-symmetric matrix, it's not true. However, for symmetric matrix, it is true. And it is very, 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 very useful. Wait for just a second. Okay, wait just 10 minutes, I will show you that. Okay, so two theorems. Okay, first theorem, and then the procedure is to prove it. Okay, so it will be mathematical. I'll try to be slow so that you can comprehend, but it's mathematics. First, I will show you all eigenvalues are real. The proof. First, S, the eigenvalue satisfy this equation. Of course, that's the master equation. So S times U equal to lambda times U. Now, I take an inner product of both sides with the complex conjugate of the eigenvector U star. By complex conjugate, I mean I take the complex conjugate of each element. And by complex conjugate, I mean when there is a number, A plus IB, if you take complex conjugate and then you change the sign of the I into minus sign. That's it. Okay. And the property we are going to use is that if a number, complex number, we take the complex conjugate equal to itself, then Z is real. It's obvious, right? If this is equal to this, then that means the imaginary part is equal to 0, and of course it's real. Okay, so you only need these two properties to comprehend the proof. So anyway, I take the complex conjugate of the vector and take a transpose so that when you multiply this, so that this U star becomes a row. So a row times a matrix times a column becomes a number. Is that okay? We call it a form, quadratic form. 之前我们把它叫做二次 form 中文不知道怎么叫，我有点忘了。但是请你一定要记得，这是一个数，这是一个数，可以吗？It's a number because this is a column, and this is a matrix. This is a row, and S times a column is a column. So a row times a column is a number. But because this kind of thing appears so often in physics, we give it, and mathematics, we give it a different name, call it a quadratic form, because it's quadratic. There are two U, so that's why we call it quadratic form. And we know how to calculate this, right? Because S times U is equal to lambda, okay? So again, the frog meet the princess, it becomes a prince. So S times U equal to lambda times U, so this number could be pulled into the front. So it is equal to lambda times U star T times U. So U star T times U is the inner product of the U with itself. Or we could call it the length of the vector, So this form gives you, if U is an eigenvector, this form will give you eigenvalue times the length of the vector. Okay. So that's this is the inner product. So it's the length of the thing. And the length of the vector must be real. By definition, it must be real because it is U1 star times U1, the first element of U. and plus U2 star times U2. This is real, so the length must be real, okay? Now, if I want to show that the lambda is real, we know this is real, and we know lambda could be real. I'm going to prove that. To ensure that lambda is real, I need to prove this is real. If I can prove this form is real, and that this is real, then lambda is real. Is that okay with everybody? In Chinese, maybe. 我现在要证明的呢，就是这个 lambda 呢是实数。所以我要做的事情 in the next paragraph 就是证明这个 form 是 real。假如我证明了这个 form 是 real， 后面的这个 length 也是 real， 那么 lambda 就是 real。Proof. Okay, so in order to make sure that this form is real, then I take its complex conjugate. It's a basic step. Every time you want to prove something, whether it is real or not, you do this test. You take the complex conjugate of a complex number and see if it is equal to itself. If it is equal, then it's real. So that's what I'm going to do here and manipulate it by a long formula. Then, so I take the complex conjugate of this thing. The easiest way for you to comprehend is write out this quadratic form in terms of the elements. Remember, this U, we call it Uj, and this S is Sij. So remember, S times U is equal to the sum over Sij times Uj. I can go back to the earlier transparency to show you why this is true. And you can also double check. Remember when I reviewed the matrix? I think it's here. Yeah, that's right. When you multiply a matrix multiplied by A, so the first element is this, you times this with this. And for the second element, you times this with this. Therefore, up here. So there's another way to write this, which is Sij times Aj. That means for the I element of this Sa, for example, my way to understand this kind of formalism is take example. For example, I could be 1 or 2. So let's say I is equal to 1. So I'm talking about the first element of the final product. The first element, I equal to 1, would be equal to 1jAj. S1jAj and sum over j from 1 to 2. That means it is equal to S11A1, S11A1, plus S12A2, S12A2. Okay, so this element is indeed could be written in this form. Okay, and for 2, if I is equal to 2, you can repeat the exercise. Give you the second one, 2, 1, 2, 1 times A1, j equal to 1, S22, 2, 2 times Aj, j equal to 2. So for I equal to 2, it's actually equal to this expression. Okay, so you can either use this geometric way to multiply two things, or you can use this more complicated, more abstract mathematical form. And in this case, it is easier to manipulate in this form. Okay, so very short review. You better familiar with yourself with these kind of expression because it will be used very often in physical calculation next year in the sophomore year. And then, so if I do the same thing here, So now that's the matrix. So SU is Sij U1J. U1 means now, oh sorry, I should go to the wrong one. Yeah, here. So Sij Uj, okay, that's the element, the ith element of Su, the column. And this column is multiplied by U star transpose. So it is multiplied by Ui complex conjugate. And then this I must be summed over, right? Because it's a row times a column. So I and I must be identified and the sum over from 1 to 2. So please convince yourself this form could be written in this form, if it's not familiar with you already. Then we take the complex conjugate of whole thing. When you take the complex conjugate of whole thing, it means you take a complex element, complex conjugate of every element. So this becomes no complex conjugate because complex conjugate becomes normal number. Because remember the complex conjugate take the sign in front of I from positive to negative. So if you complex conjugate again, negative will become positive again. Okay, so complex conjugate, they cancel each other. So it becomes Ui, Sij, take complex conjugate, Uj, take complex conjugate. That's it. We finish our simplification. Now we proceed with the manipulation. Remember, this Sij star is real. I told you already. Okay, it's a real number matrix, of course, because that's where we come from. It's a real number matrix. It's from the real world mathematics. Therefore, we don't need this complex conjugate because it will be equal to itself. It's real. Sij. That's the first step. And also, from here to here, I reverse the order of this and this. But it's okay, because they are numbers. If it is written in terms of column or row, you cannot change the order. However, if they are written in terms of elements, they are just numbers. So in the multiplication, of course, I can change the order of them and see what it comes to. So this Ui, I move it to the right-hand side, and this Uj star, I move it to the left-hand side. Why I'm doing this will become very clear. Will become clear very soon. Just follow me, okay? Wow, I mean, for mathematical proof, you have to follow the mathematician, okay? So move Ui to the right-hand side, move Uj to the left-hand side, it becomes this. But it does not look like a real quadratic form. Usually S, if here, or matrix, the index on the left will match the index on the left. The index on the right will match the index on the right. And matrix index on the left will match the index on the left, so that it becomes a quadratic form. But this is not right. J match the left, I match the right. So I better change the order. Could I do that? The answer is yes, because it is symmetric. Because it is symmetric, so Sij is equal to Sji. I can do that. That's the key of the whole proof. So remember I told you, this proof can only apply to symmetric matrix. For non-symmetric matrix, it's not true. Okay, so the key input is from here to here. I say write it down here. S is symmetric, therefore Sij is equal to Sji. So if I reverse the order of the index, then the right match the right, the left match the left. Remember, Ij is just 1 and 2. Okay, it doesn't matter what you call it. You can call it anything you like. You can call it K, you can call it L. They are just 1 and 2. 这样懂我的意思吗？ Okay, in Chinese, 你一定要记得，当我做这件事情的时候，现在的右边的 i 就跟当初的右边的 j 是一样的事情啊，因为 i 跟 j 只是我的名字而已啊。它唯一的意义就是我在求和的时候，它要等于1跟2，就这样。所以你的 i 跟 j 是什么意思，完全不重要。OK， 只要它是1跟2就行了，只要它的右边 match 它的右边，它的左边 match 它的左边，它就形成了一个 form 啊。大家这样懂我的意思吗？ It doesn't matter what we call them, it's just a notation. Okay, so even though this does not look like a quadratic form, it's J, it's I, but they are names. You can easily just replace this I with J, replace this J with I, and it becomes the standard form again. So, trust me, you can do it. This is just equal to S times U times U star transpose. Because S times U, it is this. Taking inner product with U star, it is U star transpose. Convince yourself this to this. Okay, so if you are convinced, then I'm done. Because the first step, we start with this form, complex conjugate. Now I prove that after some manipulation, it is equal to itself. So this guy is real. This quadratic form is real. So if this quadratic form is real, and the U transpose U is also real, then lambda is real. Ladies and gentlemen, I'm done. I proved the first mathematical theorem in our class, in our course. Maybe this is the first proof, the first serious mathematical theorem in our class, in our course. So, anytime you meet a symmetric matrix, you know all the eigenvalues are real. Don't underestimate this proof, because in quantum mechanics, you won't expect it. But in quantum mechanics, you are going to use almost exactly the same proof, step by step in quantum mechanics. You are going to prove in the quantum mechanics, maybe the junior one, you will prove that using almost exactly the same procedure, step by step, to prove that all the physical measurement in quantum mechanics are real. Okay, you have to prove that, because in quantum mechanics, some of the wave function is complex. So therefore, you have to make sure all the physical measurement, the number are real. In Chinese, 等到我们下学期呢开始介绍量子力学的时候，我就会告诉你所有量子力学的这个波函数。大家应该大概听说过，量子力学呢，电子呢事实上不只是一个粒子，它事实上也是一个波。那电子波的波函数呢，很奇怪哦，它事实上是一个复数 complex number。它事实上是一个 complex number. Why and how? Wait until next semester. Okay, I'm going to tell you. The wave function of electron wave is complex. But that's not good, because almost all the measurement about a quantum mechanical system must be real. The value you measure could only be real. You could not measure something like a square root of -1. It's impossible. OK， 所以呢，在量子力学里面，你必须要能够证明说，你必须要确认，不应该说证明，你必须要确认你所有所定义出来的物理的定义，它都必须要是实数才行。OK， and at that time, exactly the same proof will be transferred to quantum mechanics. Again, step by step, almost exactly the same. So don't underestimate the power of this proof. Okay, but at first, you need to understand it. Is that okay to everybody? Okay, try, and you could see some of the beauty in this proof. But at least, please understand the result, final result. All the eigenvalues are real for a symmetric matrix. Again, let me emphasize the second time, or the third time, or the fourth time. Inside this proof, except that the 2 here, Did I say this matrix is 2 by 2? No, I didn't say that it's 2 by 2. So exactly the same proof could be extended to n by n. The only thing I need to replace is this 2 at the top of the sum notation. That's the key. Every step is independent of the dimension of the matrix. Do you see that? Even though I write a 2 here, but I do not depend on this 2 for the proof. So exactly the same proof. I have already proved for n by n matrix, all the eigenvalues are real. Isn't that beautiful? That's the beauty of mathematics. You do it once, you use it for the rest of your life. Simplification, generalization. That's the beauty of mathematics. Okay, so is that okay to everybody? That's the first proof. Do I want to finish the second? Yeah, because the second is very, very similar to the first. So let's finish the second, and then we have a break. For the first proof, is that okay? More or less, right? This is probably your first experience for a serious mathematical proof. So if you don't understand it, if you feel very puzzled, that's normal. Okay, I feel puzzled when I first see this proof myself. Okay, 30 years ago. But first, you will get used to it. Okay, because in physics study, you encounter this kind of proof quite often, actually. Okay. Second, well, try to understand it. That's a kind of a gymnastic self-proof. 重训英文怎么讲 ？Training, weight training. Okay, I call it a mind weight training. Okay, I know it in Chinese, but I don't know how to put it in English. Weight training of your mind. So even though when you do weight training, the first try, oh, it's so difficult, it's so difficult, it's so heavy, I cannot lift it. But the second time, well, it's still difficult, but I can do half of it. Then the third time, the fourth time, the sixth time, the 10th time, you can do it quite easily. That's the basic of weight training, right? 重训嘛. Okay, it's the same. When you first met this kind of proof, you feel puzzled, you feel very complicated, you feel incomprehensible. It is incomprehensible. However, try it once, try it twice, try it 3 times, then eventually you will be able to understand it, and then your mind improved during the process. Okay, anyway, first proof of the first theorem, all the eigenvalues are real. The second proof is about another theorem that all eigenvectors of U, all eigenvectors of the S matrix, we call it U, can be chosen to be orthogonal. So here I have to use another index, the subscript. OK， 好，现在上面就要多加一个逐标。哦，刚刚呢我写一个 U 就行了，但是因为这里面呢只关系到一个 eigenvector。But now I have to prove that 2 eigenvector U1 and U2 are orthogonal to each other. So therefore I need a subscript. 哦，我需要一个上逐标。啊，not subscript, it's superscript. OK， 啊 ，at the upper. So SU1 equal to lambda U1. So this 1 indicate it is the first set of eigenvalue and eigenvector. Okay? And of course there will be U2 and lambda 2. That will be the second set of the eigenvalue and eigenvector. And now what I'm going to do is to multiply this equation with U2. In the earlier transparency, I multiplied this equation with itself. Now I'm going to multiply the same kind of equation, the eigenvalue equation, with U2. The other one. The other one. Okay. So now U2 transpose SU1 equal to, according to the definition, SU equal to lambda 1 U. Therefore, it must be equal to lambda 1 U2 times U1. You must be careful about 1 and 2, otherwise you won't be able to prove they are orthogonal because they are different set of eigenvectors. Okay, so U2 S U1 according to our master equation, is equal to lambda 1, u2, u1. Okay, so I'm going to manipulate the same thing, but now instead of taking complex conjugate, I'm going to manipulate the whole thing, but using the same formula. Okay, so that's why I went very slow in the first derivation, because this is exactly the same kind of expression we use here. Okay, so you could comprehend the first set, you can now proceed to do this. Now, S times U1 will be equal to Sij times U1j. U1 means it's the first set. J is the j's component. J could be E1, could be 2. So this is U11, U12. And we sum over j from 1 to 2. Then we'll get the ith element of the multiplication. And this multiplication, Su, is then taking the inner product with U2. So U2, I times I, matching the I with I, and sum over I equal to 1 to 2. Okay, it's the same thing. You better convince yourself this is the same as this. If you could not do it in class, do it at home. Convince yourself this is correct expression. And then, again, I'm going to reverse the order, just as I have already done in the first proof. I reverse the order of U2 and U1. That means I pull this to the right-hand side, I pull this to the left-hand side. I can do that because they are just numbers. You cannot pull around column vectors, but you can pull around numbers. Okay. Therefore, I pull this U1 to the front, U2 to the right-hand side. Okay, and I'm use the trick again. Sij is equal to Sji. I like to do that because now the right-hand side is I. So I like to match I with the right index. Match the left with the left index of this S. Okay, the same trick. I'm doing the same trick twice. So but I know I can do that because Sij is equal to Sji. Yeah, I think I have an explanation here. Because again, S is symmetric. S is symmetric, so I can do this. After I do this, then this is S times U. I return to the matrix notation. It becomes S times U, but now it's 2 instead of 1. So genius. So, like Trump, I always like to say, it's so genius. So S times U2 times U1 transpose. So I reverse the order. Usually you cannot do that. You cannot do that you cannot do reversing the order of column and the row. But here I could do that because S is symmetric according to this very detailed derivation. Okay? So I reversed the order of 1 and 2. So what? You may say, wow, it means a lot. Because now what the frog meet is the second princess. Again, when the frog meet the princess, it becomes a prince. But now it's the second princess. So when this frog meet the second princess, it becomes the second prince. 当你的这个青蛙碰到了第二个公主的时候，你变成了第二个王子，而不是第一个王子，不是 lambda 1 instead, it's lambda 2. That's the key of the proof. So S times U2 equal to lambda 2 times U2. Could you see that? This to this. That's the key of the whole proof. If you can do that, this lambda 2 as a prince, whether it's 1 or 2, it's a prince. Prince could move around instead of frog. Frog could not move very far, but a prince could do that. So this lambda 2 can emerge from the multiplication to the front. It's a number anyway. Therefore, it is lambda 2, U2 transpose U1. Okay, so what we got? We got this equal to this. But I have already proven this form equal to this. Ladies and gentlemen, then on the right-hand side are two expressions. Lambda 1 times this, lambda 2 times this. By this, I mean the inner product of U1 and U2. But they multiply by a different number, but they are equal. How could that be possible? The same number times different number will produce the same thing. It's impossible, unless this number is equal to 0. It could be proven very rigorously by moving this to the right-hand side or move it to the right-hand side. It becomes lambda 1 minus lambda 2 times the inner product. It must be equal to 0. So if lambda 1 is not equal to lambda 2, then this inner product must be equal. Ladies and gentlemen, I'm done. Now, this is not what I did by mathematician. Okay, I think it's from the dates back to the 19th century. So U2 times U1 equal to 0. So any two eigenvectors are orthogonal to each other for a symmetric matrix. Whatever kind of symmetric matrix it could be, any kind. As long as you can write down, I can assure you eigenvectors are orthogonal. Okay, and usually it is easiest to choose this eigenvector to be of the length 1. Choose the length, reverse it. Choose the length of the eigenvector to be equal to 1, because I say eigenvector could only be determined up to a constant. So I can choose the constant so that the length is equal to 1. Then these two vectors are called orthonormal. Also means it's orthogonal, and they are also normal. Normal means when you multiply U with itself, it is equal to 1. So this thing is usually written in this way. UMT, when you take the inner product, is equal to delta Mn. This is the basic definition of orthonormal. Orthonormal, I don't know how to pronounce it, but that's the key of the eigenvector system. Okay? That means when M and this delta function, you have to remember it. It appears so many times in physics. Delta Mn means when M is equal to N, it is equal to 1. If M is not equal to N, it is equal to 0. Okay? So the right-hand side ensures that M is equal to N. Otherwise, it vanishes. Okay, so therefore, it means the inner product of this and this will only be equal to 1 when they are the same eigenvector. If they are different eigenvector, for example, this is 1, this is 2, this is 1, this is 3, this is 2, this is 3, delta Mn will ensure they are 0. The inner product is equal to 0. Is that clear to everybody? Even though you don't understand the proof, it's okay. I say it can take 3 times, 10 times to understand, but the final result is so important. The eigenvectors are also normal. I can choose the eigenvector to be this way. Okay, let's do it this way. Final reminders. Remember, all the proof are not dependent on n equal to 2. Only here, 2 and 2. Of course, this is 1 and 2. Of course, that's because in 2 by 2 matrix, I have only 2 eigenvectors. However, it is trivial to extend all the to generalize all the proof to n larger than 2. Okay, the only thing you need to do is to replace this by the number of the matrix, the dimension of the matrix. Okay, it could be 3, it could be 4, it could be 5, it could be any large number. The proof is still true. Okay, different eigenvectors are orthogonal, and we can choose it to be normal of the sense equal to 1. Okay, so let me finish the final comments, and then we'll have a break. You may say, so what? Yeah, this is important, let me tell you. Because with this kind of orthonormal vectors, I can easily decompose any vector in terms of a linear combination. Oh, I have used this already before, right? I decompose any vector that we call it x into the linear combination of u1 and u2 in the first in the first part of my lecture today. So, written in another form, any vector v corresponding to the capital X in the earlier talk. So v, any vector, could be expanded into C1 U1 plus C2 U2. How could I be sure this is possible? Let me answer you. It is because I can write down C1 and C2 for you. How? It's easy. Just take the inner product of V, this vector I want to talk about, and the first eigenvector, sorry. Remember, if this V is decomposed in this way, and taking the inner product of this, then it could be written as C1 times U1 inner product U1 plus C2 U1 inner product, sorry, C2 inner product of U1 and U2. And it's complicated, but it's not. I have already told you that this is equal to 0. This is equal to 1. Don't you remember? Here. Okay, so when I take the inner product of U1 with the vector, I only pick out the part that is proportional to U1. Is that okay with everybody? So when I multiply this U1 with the vector, I only pick out U1 in the linear combination. Okay? Because this multiply this equal to C1 U1 U1 plus C2 U1 U2. U1 U2 equal to 0, orthogonal. U1 U1 equal to 1, also normal. Therefore, Therefore, C1 is equal to V dot U1, or I should call it U1 transpose times V. Ladies and gentlemen, I determine C1. And if C1 is determined this way, C2 could be written in almost the same way by multiplying V with U2. C2 equal to V dot U2. Done. So I determine C1, I determine C2, then of course the V could be decomposed into a linear combination. Of course, this is so cute. So it has a name. It's called expansion theorem. Any vector could be expanded in terms of eigenvector. This is called expansion theorem. Of course, ladies and gentlemen, this is from your kindergarten course. This is taking a projection. 这就是找投影啊。在学向量的时候，你怎么样子来算一个向量在轴上面的投影？那时候我们把它叫分量嘛，分量就是投影嘛。你怎么算它的投影？很简单，你只要把这一个向量跟单位向量 x 轴方向做 inner product， 老师以前就会告诉你说，这就是把它投影在 x 轴上面 ，and you got 的第一个分量。你把这个向量呢跟这一向量跟这一y 方向的单位向量做投影，你就得到第二个分量。Exactly the same thing we did here. 在哪里？在这里。C1 V projected to U1, C2 V projected to U2. Okay, so U1, U2, the two eigenvectors are almost like unit vector in a coordinate system. 再一次 in Chinese better. U1 跟 U2 这两个本征向量，就好像是一个正交的坐标系统的两个单位向量一样。所以你如果想要知道一个向量在上面的投影，你就直接做内积就好了。In English, these two eigenvectors are just like a unit vector in a coordinate system. So if you want to know the components of vector along the two axes, you just take inner product. There is an official name, It's called taking a projection. You're taking a projection of vector along the two directions, and then you got the components. That's exactly what we did here. Again, let me emphasize it the 10th time. All the procedure could be extended to n by n matrix. 不是只有对2乘2的矩阵才对。Okay? Yeah, that's probably it. Okay, good. Let's take a break. So, two theorems. First theorem, we prove that for symmetric matrix, all the eigenvalues are real. We prove that all the eigenvalues are perpendicular to each other. And we use this perpendicular to each other property to prove the expansion problem. That's the essence of our talk today. I'll follow by another theorem, but the third theorem is much simpler. But remember, we haven't finished yet. Remember, we need to prove the eigenvalues are real and positive, the lambda. Because that lambda, if lambda is not positive, then it will decay, right? So 我们还没有完成，我们需要证明 lambda 是正的。我们已经证明它是 real， 我还没有证明它是正的。We'll be finished very soon in 10 minutes after our break. Okay, let's return at 11. Okay.